The second part of heat energy is related to changing state. It takes energy to lift something to a higher height. It takes energy to make something move faster. It takes energy to increase the temperature. Similarly, if you've got a solid, it takes energy to melt that solid. And if you've got a liquid, it takes energy to evaporate or boil that liquid. Okay, this is the world's most boring lab, and I'm not even kidding. I used to do it in class. I would set it up like the night before, but I would put a beaker of water in the freezer. I'd have to use a special beaker that didn't crack, and I'd jam a thermometer into it before it froze. Then I'd bring it into class, and I'd put this beaker on a Bunsen burner, and I would slowly heat it up until the water was all boiling. Well, until the water was boiling. So literally, the lab was melting ice. Because I wanted to get the graph, I did it slowly, so I'd like be teaching in the background, but literally this was a demo I used to do in class. We would literally sit around and watch ice melt. The goal of the lab, the whole learning point out of it, is we generate a graph with temperature on the vertical and time on the horizontal. So kind of like this graph down here. We couldn't do this whole complete version of the graph in classroom. This graph assumes it went to steam. When I did it in class, we would just get it to boiling. So we get this part, then we get this part, then this part, and then this would be boiling. I couldn't get this part. What do you think was going on at those flat parts of the line? It's still sitting on the Bunsen burner. So from B to C, from D to E, this block of H2O is on the Bunsen burner, but the temperature, like energy is leaving the Bunsen burner from that gas into heat, into that water, but from B to C, it's not increasing the temperature. D to E wasn't increasing the temperature. This is a classic lab. This graph that I've generated gets called a heating curve. As boring as it is, it's got lots of cool physics that people can pull out of it. What we're going to pull out today is these flat parts. What's going on these horizontal plateaus from B to C and from D to E, that's where the change of state is happening. Here I'll talk you through the whole graph. From A to B, it's ice, and it's going from like -10 to 0. So there's an increase in temperature, they're negative numbers, from negative whatever to 0. But at B, this is where it gets to 0, so it's at the start of B. At the start of B, it's still solid water, but from B to C over this time, all the ice melts and it goes from being solid water to liquid water. So the energy that was being added by the Bunsen burner didn't go into increasing the temperature. The energy went to increasing some other sort of energy that made it change from solid to liquid. In chemistry class, sometimes we talk about degrees of freedom or ability of the particles to move around. The liquid particles have a bit more freedom to move, and it takes some energy to give them that freedom. So in that flat part from B to C, the energy of the Bunsen burner wasn't increasing the temperature, it was giving those particles that extra energy that they needed for that extra degree of movement, for that extra vibrational energy or whatever the chemistry says that they've got there. So B to C is a temperature change, specifically solid to liquid. Then at C, all of the ice is now in liquid form, so the Bunsen burner energy from C to D goes into increasing the temperature from 0 to 10 to 20 to 30 to 40. By the time we get to D, we're at 100 degrees. Similar to what happened to B to C, we're at a phase change place. The energy of the Bunsen burner is still being added, but instead of going to changing the temperature, the energy of the Bunsen burner is being used to give those particles that extra degree of freedom, that extra move around energy, as I typed it there. So the energy is still going into those particles. The energy is still going into the particles from D to E, but it's not increasing the temperature. Then we can't do it at class because it would build up gas and pressure and all sorts of other things. Definitely don't do it at home if you're playing along. But if we could heat it up more, after E, all of the H2O would be in steam form. And if we kept running the temperature, we could get like superheated steam, like 110, 120, 130. Dangerous because pressure is involved, dangerous because of the high temperatures. So we would never do it at school. We don't have the right equipment, and that's not worth the risk. But that's in theory what would happen next. If we really cared, we could do lots of cool things with this graph. The slope from A to B is related to the specific heat capacity of solid water, because that's where it was ice. The slope from C to D is related to the specific heat capacity of liquid water. It's not exactly the slope, it's just the slope would communicate which part had a higher specific heat capacity and which one had lower heat capacity. Similarly, if we kept it going, the slope over here from E to wherever we chose to end this lab, the slope, the steepness of that would communicate the specific heat capacity of the gaseous form of water or whatever material we're looking at. The other cool part that we're going to pull out today is these two flat parts, the horizontal parts from B to C. That represents the energy it takes to change state from solid to liquid. And the energy from D to E, that represents the energy it takes to change state from liquid to gas. Because we kept adding energy to the system, to the water, let's say, but the water wasn't changing temperature, they gave this a funny name. They called this the latent heat. So it's all in here. I think this is all, sorry, I didn't do my homework, I didn't read this all through. That's called a heating curve, we talked about that. That's change of state. I'm going to jump to down here. Oh, this is kind of important. To turn a gas into a liquid or liquid into solid, so if we kind of go backwards by cooling them down, so let's say you've got water and you want to turn it into ice, you've actually got to take energy away from the water to turn it into ice. That's all up there. You read that. I want to jump to this. This confused people originally. We were adding energy to the liquid, but the energy wasn't showing up as a temperature change. The energy was hiding. So when they described this energy it took to change state, since the energy was kind of hiding, they used an old word for hiding called latent. So we're going to call it the latent heat. Latent heat is the number of joules. It's the amount of energy required to change state from solid to liquid and then liquid to gas. If we're going solid to liquid, we have to add that many joules. If we were to go backwards and go from liquid to solid, that's how many joules we'd have to take away. That energy is being added, but it's kind of being hidden in the movement of the particles and not an increase in temperature. Latent heat has a rather simple equation. It's a constant. We call it the latent heat. There's going to be two of them, and the energy it takes is just the mass times that latent heat property. If we're going from solid to liquid, then we use a latent heat called the latent heat of fusion. That would be related to this first B to C flat part of this graph. That's the fusion that's going from solid to liquid. If we're concerned with going from liquid to gas, that was the other plateau, it would have a different quantity. It takes a certain amount of joules to melt water or melt ice into water. It's going to take a different amount of joules to take the same amount of water and have it go from water to steam. The two different phase changes don't have the same constant. It's related to the size. Generally speaking, when you start Googling them, it takes more energy to boil something than melt it. So often, the one we call latent heat of vaporization, the constant that tells us how much energy to get to steam, is a bigger number than the latent heat of fusion, which is the amount of energy it takes to go from solid into liquid. In a way, it's a simpler equation. There's just two quantities. If I tell you the M and what phase change, you can find the L, multiply those two together, and that tells you the amount of energy. I don't know if that was my best jabbering, but that's where I'm going to pause. Take a look at the two examples and definitely make sure you take time to pay attention to those solutions because I think I do a little bit of a better job explaining it there. Here's the worksheet that I mentioned in the last video. At this point, you can do that whole worksheet, and there's one check-in related to heat energy. Email if you have any questions. Take time and go through the videos. I don't think it's as confusing as this video maybe made it sound. Email if anything's bugging you, and good luck with it.